We'll start with a quick recap. So we've defined sigma algebra on a set to be a collection of subsets of the set that contains the empty set and the entire set, although we don't have to say that, that is closed under countable unions and automatically under countable intersections, and closed under complements. And we have also defined for any collection of subsets of a set X, we've defined the idea of the sigma algebra on X generated by that collection. So the sigma algebra on X generated by F can be defined to be the smallest sigma algebra on X that contains F, which there is a unique smallest sigma algebra on X that contains F. You can also describe it as the intersection of all the sigma algebras on X that contain F. That's pretty much everything we've done so far. Now I want to introduce what I'm calling Lorillary 128.5, and I'm giving it this silly made-up name because it's a merging of lemma 128 and corollary 129. So here goes. Suppose you have a function of sets, f from x to y. So any sets, x and y, any function. Very general situation. Now, I'm going to use script A, like this, to talk about sigma algebras on X, and I'll use script B, like this symbol, to talk about sigma algebras on Y. So I'll always use those symbols. Now this lemma corollary is all about moving sigma algebras around between X and Y when you have a mapping F. So the first item is about pulling back a sigma algebra from Y to X. So suppose you have a sigma algebra on Y, call it script B. Then if you take the collection of preimages of all the sets in that sigma algebra, which we call measurable sets, when we have a set in a sigma algebra, usually you call it a measurable set. So if you take the preimages of all the measurable sets on Y, then that collection of subsets of X is going to be a sigma algebra on X. And I'm using this notation because it's nice to have a notation to describe this construction. I think the textbook just doesn't introduce this, and to be honest, I made this up, so I have not necessarily seen people use this in analysis, although they might. This is borrowed from geometry and other fields where people use a superstar like this for pulling back a structure along a function, and a lower star like this for pushing forward a structure along a function. So this is the definition. F upper star of a sigma algebra on the codomain of F is going to be this thing, which is a collection of subsets of the domain of F. And part one of this result is when you do this, you get a sigma algebra on X. Then part two, this I'll call, so where I'm calling this one up here the pullback of a sigma algebra on Y, this here I'll call the push forward of a sigma algebra on X. So to pull back a sigma algebra, I took the preimages of all the measurable sets, of all the elements of the sigma algebra. To push forward a sigma algebra on X, you might expect that I would take the images of sets, right? But it's not so. It turns out image is just not a good operation. Preimage is a lot more useful for this kind of thing. Preimage interacts a lot more nicely with unions and intersections and complements compared to image. So here's what turns out to be a useful way to define the push forward of a sigma algebra on X is collect all those subsets of Y whose preimage is measurable. So where here we take the preimages of the measurable sets to go from subsets of Y to subsets of X, here we collect the sets whose preimages are measurable to go from subsets of X to subsets of Y. And our second result here is that this does form a sigma algebra on Y. And then finally part three is about sigma algebra generation. If you have some collection of subsets of Y, then there are two orders in which you can do things. First, you can use it to generate a sigma algebra, then you can pull that back and get a sigma algebra on X. Or you could instead pull back these generating sets, pull back the individual f's in script f, and then generate a sigma algebra on the set X. So here, if I put in the full decorations, this would be sigma algebra generation in terms of sigma algebras on Y, and then this one is happening on the X side of things. And our third result is that these really do give the same. These really do end up being the same. So this is going to end up being really useful, and we'll use it to define some very important sigma algebras. Okay, so let's prove this in the next video.